Now before we go on and generate these models of dispersive wave propagation, we're going to start with a single frequency wave. So here is a harmonic wave in real space. We can write it down as a cosine function, so cosine k0x minus omega naught t, and the speed of the wave is c, which is the ratio of omega naught to k0, and this is a constant. We can expand this cosine function as a sum of complex exponentials. That makes it a bit easier to take the Fourier transform, and we're going to take the Fourier transform of the spatial dimension. So we're going to transform x into k. Anything with a t in it is going to be just basically treated as a constant. So taking this Fourier transform, so I've got capital F, k, and t, we have the complex exponentials with k0x being transformed into delta functions with a factor of pi out the front, and so we get delta functions at positive and negative k0. So that's what these spikes are here on this right hand side. This is now the Fourier transform, and so these spikes here, these arrows, represent the delta functions. Now the delta functions also have this complex exponential out the front of them. It depends on time and omega naught. There's a negative and a positive here, and what this is going to do is rotate these delta functions around in the complex plane as a function of time. So we can animate this and have a look. We see our wave moving through real space at speed c, and over here in the Fourier domain we have these delta functions at positive and negative k rotating around in the complex plane at a speed determined by omega naught. So what we've discovered is that the motion of the wave in real space corresponds to rotation of these k components around the complex plane in the Fourier space. Now this is something that we can understand from a different perspective, that is via the shift theorem. So the shift theorem is something we can use for a function that is translated in space or time, depending on which domain we're thinking about. So let's take a cosine function and shift it by an amount delta x in space. The shift theorem tells us the Fourier transform of a shifted function is equal to the Fourier transform of the unshifted functions multiplied by this complex exponential that depends on the amount of shift delta x and k. So if we apply this to the cosine function, which has been shifted, then we get this Fourier transform here. So we get our delta functions back, and now we get these complex exponentials with a negative k0 delta x and a plus k0 delta x. Okay, so here we have this shifted cosine, and here we have a cosine that's rotating in space with some time dependence. So how are these two functions here related? Well, they're related by the velocity of the wave. So we have, in this case, a cosine wave moving with velocity c, and c is equal to omega naught on k0. If it moves for a time t, then the translation will be delta x equal to omega naught on k0 times t. Substituting this into the expression we've derived here with the shift theorem gives us the Fourier transform we derived for this cosine wave up here. So the motion of the wave in Fourier space corresponds to this rotation. It's rotating at a speed omega naught, and the size of omega naught, the bigger omega naught is, the faster it will rotate. That also makes the speed faster here, because the speed of the wave is omega naught on k0, which would mean it would move further in space. So this will become important. This speed of the wave becomes important when we start treating multiple frequencies with dispersion, because the speed will not be constant. It'll depend on the frequency of the wave. Let's just do that same analysis now for a wave that is composed of two frequencies added together. So we've got a cos k1 omega 1 and a cos k2 omega 2. The ratio of omega and k for each of these waves is the same. It's the speed of the wave, and that's a constant. There's no dispersion. The different frequencies move at the same speed. So when we do the Fourier transform from x to k, we get this expression here. Now we have delta functions at plus and minus k1 and plus and minus k2, and each of these is being rotated at the right frequency in the right direction. So the k1's rotating at omega 1 and the k2's rotating at omega 2. So we look at this and see what happens. So here's our wave moving in space in x, and here's the wave moving in the Fourier domain. What we see is that these components at these different values of k rotate at different speeds. So the further you go away from k equal to 0, the faster it rotates. And we know that because the speed of rotation, omega here, is equal to c times k. And the speed at which they're rotating is linearly proportional to k, and that's because we have a wave with no dispersion, and the ratio of omega and k is a constant. In terms of the shift theorem again, the time shift rotates the phase in the Fourier space by the amount omega I times t, which we can rewrite as ki times c times t, or ki times delta x. So this rotation by omega I t corresponds to the motion of the wave by amount ki times delta x, and delta x depends on the speed of the wave c. And because the ratio of omega and k is a constant, both frequencies travel in the same distance delta x in any given time.